Hi, I'm Dylan Lawrence, and this is our truss presentation of our ENGR220 project. We are the underwater basket weavers. So the purpose of our project was to design the most efficient truss possible with the material given, and also to analyze all of the aspects of the forces that we have learned in class. Here you see our truss design. It is composed of dog-bone-shaped members. The reason behind this is the rounded edges prevent excessive stress and tear out at the end. You may wonder why members GE and AH are so thin. This design actually ensures that all the members undergo the same amount of stress.
My name is Nisha Siriwardane, and I'll be going over the dimensions and figures of our truss members. In this table, you can see our calculated width, length, and area of our truss. Our length was found based off of a height that we set on our truss and also a 60-degree angle that we placed at either end of the truss. Our width is based off of the proportional force going through each member by the force loaded 14 inches from the left. The force that we calculated our data off of is 100 pounds. From here, we calculated our moment of inertia and total forces, and axial stress and tensile stress. On this slide, we have the calculated tensile stress in the gauge and hole, and also the tear-out stress and the predicting buckling load. For each stress, we have our factor of safety also calculated.
This is Michael Kohlmeyer, and this slide is for sample calculations. For the first calculation we did, we calculated the reaction forces of the truss. To do this, we calculated a moment around A by summing all the moments equal to 0. The first moment would be the moment created by the force on the truss. You multiply that by the horizontal distance from A, and then you add it to the reaction at D, multiplied by its horizontal distance from A, and then you solve for the reaction force at D. Next, we calculated the force in member AB. We did this by setting the reaction force at A equal to the y component of the force at AB by multiplying it by the sine of its angle. And then we solved for the force at in
I'm Caroline Bell, and I'm going to talk about truss failure. We predicted that failure would occur in the member throughout at one time because we had designed it to where there was equal stress within each member. However, the failure occurred in member DE at 90.7 pounds because of torsion, which our issue was not calculating the Euler buckling load prior to designing, and our failure conclusions are that shortening the height of the truss and connecting the trusses diagonally would help prevent torsional failure. In order to improve the project, we decided that maybe a preview of questions to have the students think about the project and really try to come up with a bit of a design, but not at the same time. They would look at all the shapes that they could use for each member and try to decide what shape would be best to support the most force. And you could ask questions about what shapes would be possible, which would be best shapes, how to reinforce the members most appropriately, and maybe sketching a design of the truss that they might use.